this. Thank you for this opportunity. I'm going to talk about laser remote sensing and Lidar applications and some of the future trends on this. This is more from a personal viewpoint. I'll try to cover some of the different subjects in the back, so you can get an appreciation of what has happened in the past and sort of where the future is going. Sort of the outline of my talk. We'll talk about ranging and spectroscopic aspects of Lidar, as Lidar or laser remote sensing, or sort of some past examples so you can see what the size is and what they were doing and what the complexity is. I'll give you some examples of differential absorption Lidar that is used a laser beam to measure CO and CO2 in the atmosphere. And then some more commercial ranging and mapping Lidar that's being developed now. I can't cover anything at NASA, but I can show you some of the programs that they have. There are many large satellite systems using laser remote sensing, including NASA and also ESA, the European Space Agency, and other countries, Japan and other people. And then some of the trends I want to go over, some of the smaller size ones, multi-wavelength Lidar being used in drones or just a single wavelength Lidar. And then the importance of integrated photonics, which is making them smaller and cheaper. Let's see, okay. This is a sort of a picture of what laser remote sensing is, sort of a cartoon. You have a laser beam, you send a pulse of light out into the atmosphere. It bounces off of hard targets or the atmosphere itself. And then, so you're really using the laser beam as a remote probe or a remote chemical probe of the environment. And I like to say it places a spectroscopic chemistry lab at a distant place. And you're able to have ranges of about, from a meter out to 10 kilometers or further on out with this. The ranging aspects of Lidar are easy to understand. If you send out the pulse of light, it will travel with the speed of light, which is about 1 foot in 1 nanosecond. And so when the back scattered light comes, when you sense that with a telescope and a detector, you're able to measure what that distance is out to the target. And so this is a pulse laser. There's another way of measuring it using FMCW lasers. You're looking at the Doppler shift and the frequencies shift on that, but but both of those techniques in order to measure the time of light going up. Okay. Now there's also spectroscopic aspects of Lidar. The laser beam can act as an optical probe of the diameter. The wavelength of the laser, it helps to determine the information that you're going to be looking at from the target area spectrally. You can also do a standard chemical optical analysis. You can look at the wavelength shift of the reflected light. You can look at fluorescence emission, Raman emission. You can look at the absorption of the light. And what I put down here, just to put in a clue, because there are the possible errors, normally we know the wavelength of the light to about 10 to 11 significant figures, but it's the intensity that may not be known. It's like, and the reason that's important because that is related to the concentration of this intensity is only known to do calibration through the window out into the air. You also send some of that beam through an absorption cell in the laboratory in order to have a calibration. Now, with these different kinds of techniques, we can classify Lidar into different ways. And here's one way. Classical LiDAR is when you're just looking at the ranging out to clouds and hard targets. A Doppler LiDAR, it measures the small, but you're able to see it target speed or the aerosols. And so from that, you can, from the Doppler shift, you're able to measure whether it's the speed of the air or the target. There's differential absorption LiDAR, we call it dial, but you're really measuring the difference in absorption due to gases in the atmosphere. And what you do is you send out two different wavelengths of light. One's absorbed by a species in the atmosphere and one is not. And from that, you can measure what the concentration of the species is. You all can also do fluorescence LiDAR. You can detect the weak fluorescence from surfaces and gases. And this works very, very well when you have an isolated substance that gives off a fluorescent spectrum that is separate from other species that may be interfering with it. One of the best fluorescence LiDARs is we use the sodium that's up in the upper stratosphere. There's about 2 kilograms of sodium floating around the world, and we're able to hit that with a fluorescence LiDAR, make the sodium spot glow. And then what we can measure sodium with that. We can use that for measuring waves around the Earth. We can also use it as a beacon for atmospheric correction for turbulence in the atmosphere for telescopes. You can also use Raman LiDAR. But the Raman emission is rather weak, but if the substance or the gas has high concentration, then the Raman lines are fairly strong. And you can also do LIBS and filamentation LiDAR. LIBS is laser-induced breakdown spectroscopy. And filamentation LiDAR, you use the laser, focus it down, and make a spark in the atmosphere. And then from the emission from that, you're able to see what the atoms are and what the molecules are. So with that, if you look at the effective LiDAR backscatter values, I put this in so you can see that the backscatter from a regular hard target, the effective backscatter is maybe around 10% to 50%, something on this order. If you use a retroreflector mirror, that ups it by about 4 to 5 orders of magnitude. If you're just looking at the atmosphere, the scatter from the air in your hand, shall we say, that's down by about 4 to 5 orders of magnitude. If you look at fluorescence emission, it's very, very small in the infrared, but in the UV, it's around 10 to the minus 2 on a relative scale here. And then Raman scattering is even less, it's around 10 to the minus 9. So in the case of the Raman scatter, it's best if you have high concentrations of the species, like a solid or a liquid. Now, you also have to look, take into account the spectral transmission of the atmosphere. This is the transmission of the atmosphere over a 2.8 kilometer path from about the UV around 0.3 microns all the way out to around 15 microns. And you're able to see, the openings in the atmosphere where there's transmission. Here in the visible around 1.5 microns, 2 microns, and then also at 3.3 to 4 microns, that's the fingerprint spectral region where many of the overtone bands of organics and compounds exist. And then out from around 9 to 10 microns or further out. Okay, this kind of gives us this is a low resolution spectrum of the atmosphere. A high resolution looks more like this, and this I just put this in. This is from some stuff I was doing on laser communication through the atmosphere. This is the transmission of the atmosphere around 0.8 microns, around 1.5, and also at 9.5. And you can see the individual absorption lines of the of the gases in the atmosphere: water vapor, CO2, ozone, oxygen, and other molecules, CH4 and other things. And so if you're able to isolate the laser wavelength to one of those absorption lines, and the absorption lines are always around about 1/10 of a wave number in width. And so you can tune the laser across that absorption line and then measure what the concentration is of the species, which is the dial technique I was talking about. Now, some of the early LiDAR history, I put this in Now, the earliest laser, of course, was, the first one was a ruby laser by Ted Maiman at Hughes in 1960. But there were several other groups that made lasers the next year. I know Bell Labs did. Ford Philco had a large group, and also Raytheon did. And the reason I bring that up is because the next year, in order through a large telescope, and this is out at MIT at the Lincoln Lab group, and they use a flash lamp ruby laser with a pretty good, a lot of power, 50 millijoules, but it wasn't Q switch back then. They didn't know about that in 62. And so they shined it at the moon and got the return signal. It was delayed by 2.5 seconds, the time going out and coming back. But they only got a signal of around 12 photons, and they had to use huge amounts of Polaroid film in order to measure photographs of the oscilloscope in order to see where this actual signal. But what's sort of neat is the next year they invented the Q switch for lasers using a rotating mirror and increased the peak power by 4 to 5 orders of magnitude. And so the return from the moon was large, and they're even able to see the returns from clouds in the upper atmosphere. So this is one of the earliest lidars. A photograph of this, this is kind of neat because this shows the 3 main characters for this, and that is Professor Smulin on the left, a physics in applied engineering professor at MIT, and Stan Cass, who was at Raytheon, the laser guy, and then also Giorgio Fiocco from Italy. And at the time, he was a radar scientist from Italy, and they happened to be together. And a large telescope at the Firepound Observatory up at Lincoln Laboratory that the Professor Smulin was able to get hold of. And so then they took the laser beam, and they're showing it here going. This is a little speck up in there, and that's the moon. And that was the first time of a LiDAR beam coming back from the moon. So, well, then after this was shown that it was possible, there are a lot of other LiDAR sensing stuff that was done. Dick Shotland at University of Arizona was the first to do a dial system. He measured water vapor in the atmosphere. He tuned a ruby laser by changing the temperature of the ruby rod, and this changed the wavelength, and then tuned it across a water vapor absorption line. And then since that time, thousands and thousands of different LiDAR systems have been used, for looking at various gases and targets. And just put this down that started the Laser Radar International Laser Radar Conference. It was started in 1968, and it's biennial, and it's been held every year, every 2 years since then. Of this, some of the LiDAR examples I want to show you here, just so you get a feeling on this. Here's I'll show you one of the large LiDAR systems that I worked with. We used 2 CO2 lasers, frequency doubled them, and this for the dial sensing of CO across a roadway. I want you to see how large this LiDAR was on that. And then later, about 20 years later, this was a laser that we developed at 2.0. Then I'll show you some examples of LiDAR mapping that people have developed, because this is sort of where the work is being done now, and then some composites of satellite systems that NASA and ESA have on that. This is a photograph of our large laboratory size LiDAR system that we had. And this, you got to remember, this is 40 some years ago, but look how large it is. But that was just the state of affairs. And also on top of this lab was a large telescope. This one here shows it going out the window, but we also had a system was by tuning across the wavelength, the other was absorbed by CO in the atmosphere and one was not. This was a laser beam was then sent across a roadway that was half a kilometer away, and you're able to see in real time the increase of CO in the atmosphere due to automobiles going across the road in the morning rush hour around noon when we went out to lunch and in the evenings coming back. So this just shows, you know, some of the capabilities are of a large LiDAR system. A more modern one that was we developed was a highly tunable, smoothly tunable holmium-YELF laser. This shows the schematic of that. We had an argon laser pumping a Thai sapphire, pumping a holmium-YELF laser that we developed. And then you go through, you put into wave meters and interferometers and spectrometers, and and IR video cameras, everything in order to monitor what the wavelength is on that. But with that, we were then able to tune it smoothly. This is a picture of the transmission of the atmosphere over a path of about half a kilometer, if I remember right on this, but showing around 2.06 microns. And these are the absorption lines due to CO2 here. And this overlaps the tuning range of this holmium-YELF laser that we and off one of typical data. We took the laser beam, ran across our college campus here, brought the beam back off a target, and by tuning across the P18 absorption line of CO2 in the atmosphere from this depth, and from the background here, we measured that this is 460 parts per million of CO2. And what we found was that the CO2 level would also vary slightly according to some of the chemical things that were happening in our asphalt parking lot. Some of the hydrocarbons were developed more by NASA. LiDAR system is here. This is a little bit later. This is one at Optech Corporation in 2010, Alan Carswell's company at that time, later bought out by Teledyne. This is it puts out around 200,000 laser to then look at the hard target. They would put this into a helicopter, an airplane. As an example of this is the LiDAR mapping of power lines and trees near a power station. And what I like about this one, it shows not only the, because the laser beam is only maybe about 1/10 of a meter in diameter or less, you can focus it down. You're able to pick up the power lines. And then this also shows from the ground that has penetrated through the foliage. And so you're able to measure actually what the height of the trees are from the ground up to the top of the foliage levels with that. Well, this is a typical system of, this is in an aircraft, in a helicopter. A more modern system, and I just put this in so you can see what's currently being done. This is a modern mapping LiDAR that weighs about 5 pounds, and it is being flown around by a drone. And so it's able to do the similar thing that I just showed you earlier with the Optech system, but it's able to move over the terrain. And this is an example of the 3D here. This is the 3D point cloud that is able to measure here, and then this, from buildings and dams and other things. And so I put this in so that you appreciate that LiDAR mapping is really a very large business now, and the whole field is, by down. And so you're able to measure things to the accuracies of a few centimeters. And plus you're able to fly wherever you want to in order to check out these places. It's very important. Now, some other systems, large scale ones are shown like in this one. This is from at NASA, the Earth Science Group there. This is a nice photo, a nice diagram, I should say, where they're showing all the different Lidar systems and, well, all the different remote sensing systems they have put into satellites and also the International Space Station. And since about 1995, I believe is here, and then planned out to 2033. And I point these out because there are so many nice large systems that they have planned or are flying in order to give us a better view, and the capability in order to see what is happening on the Earth. This another one which is in more detail. This is from the ESA Aladdin Doppler Lidar system, and this was launched by the European Space Agency in 2018. And I put this in because this has such a nice picture of the Earth, and then the Doppler, the wind speed that they're able to measure, and then the satellite. I just like that sense of that. But with that, they're able to sense global sensing of winds. And this has been a dream of people in atmospheric sciences for decades, because if we can increase the measurement of winds on the Earth, then we're able to increase our weather prediction, and both the accuracy and how far out that we're able to do with that. So these are some of the examples. Some of the things I've tried to show is some of the Lidar, what I call conclusions from this. Lidar and laser remote sensing is able to measure many environmental species. Ones I haven't shown, but CO2, CO, HCl, methane. There's about 20 different species that they've been able to measure in the atmosphere. You can map out hard targets, from very short ranges out to long ranges. There are many significant advances have been made in the development of new precision tunable lasers and spectroscopic techniques, and they have been applied to remote sensing. And I just want to emphasize it's very important to measure the spectral interaction of the laser waveform and the absorbing species in order to determine the chemical properties, i.e. the concentration of that. You can also look at some of the main progress during the past 60 years has been driven by the new laser developments, new tunable lasers, new smooth wavelength control, injection seeding, solid state, quantum cascade lasers, and right now the current ones and the best ones are frequency comb lasers that are given a precision of knowing exactly what the wavelengths are and what the absorption spectrum is. The precision control of laser frequencies, line widths over this, new spectroscopic techniques I haven't talked about, the saturation fluorescence, and multi-detector coherent addition. We've worked on that. What is really great is data processing. The computers used to be this big and now are nice and small. And looking at drone interconnections of drones and constellations, and people are working on this. And what I like to emphasize the reduction in Lidar system size. We started with a lab, with a lab size system that has, 3 or 4, optical iPhone 13 has a VCSEL laser lidar or a laser radar, that measures your face. That's the reason you don't need to press a button anymore. It does a lidar contour of your face, and that's the ID part on it. But that's a lidar. It's VCSEL lidar, vertical cavity surface. ESA and NOAA, and they have large programs for measuring, around the Earth. There's the dial systems, Aladdin, ones for looking at CO2. There's also new precision tunable lasers. I've talked about this. Significant growth. I'll try to talk about this a little bit, but the mapping LiDAR drones, and then the large, and this is a large group here, but autonomous vehicles, driverless cars. We've gotten the laser systems down to about $100 a piece. In real time at 30 frames a second as the car is driving down the road. So you map the light, you merge the LiDAR system along with along with cameras and radar, and hopefully we're able to get a driverless car. And there are many companies that are working on this very, very well now. And so some of the more current trends that as I see them, shorter range LiDARs on drones. I want you to point out that they are less affected by atmospheric transmission as opposed to a single long range LiDAR sensor. So you see that you can see the move to short range LiDARs for targets, because you can take the LiDAR, put it on a drone and fly it over to where the area that you're trying to sense is. You don't have to have one LiDAR that will do everything. The next part, which has not been done yet, what I see it, is multi-wavelength spectral Lidars will be used in drones and ground-based sensors, because when each Lidar is $100, I can put 10 of them together and I can get a hyperspectral. I can get 10 different wavelengths, and from that I can measure what the differences are in the fluorescence, the Raman, or the absorption. And finally, integrated photonics. They are being developed quickly for autonomous vehicle LiDAR systems, but they will be used in these multi-wavelength, what I call hyperspectral LiDAR sensors that will be coming out. And so with that, I want to thank you for hearing this, and I hope if there are any questions, that'd be great. Thank you.